Hey everyone, welcome back. Thank you for joining me again. I hope you're all doing well. I'm doing fantastically. So, what better time to talk more about set theory, more about set identities. So let's continue our discussion of that and really get these concepts down. So, let's get started. So last time we were talking about the rules of set identity. So let's continue talking about that. But I want to start with the most important rule of set identity. And these rules are called De Morgan's rules. They're about negation, how negation and intersection and union all interact with each other. It's probably the most important rule for set identity, so let's get a handle on it. So let's get started.
So let's start talking about De Morgan's rules. So who was De Morgan? De Morgan was a British mathematician who lived in the 19th century. He wrote a lot of important work about logic, about set theory, about trigonometry, and also about spiritualism, clairvoyance, and the paranormal, which is not really what you'd expect from a mathematician, but, you know, sort of interesting. So, what do De Morgan's rules actually say? So basically, De Morgan's rules are about the connection between the union and the intersection operators and how they can be defined in terms of each other. So let's have a bit of a look at how it all works. So the basic way to sort of understand De Morgan's rules is by this. So let me just write it out. Okay, so the complement of union or intersection is the other one of the complements. What does that mean exactly? So the complement of a union is the intersection of the complements. Or the complement of an intersection is the union of the complements. Whatever you plug in this slot here, if it's union or intersection, the opposite is going to be in this slot here. So this is really showing that the union and the intersection are the inverses of each other. So let's look at it in action. So let's start with the first one up here. So we've got our universe and we've got two sets, A and B. So let's say this one is A and this is B. So if we wanted the union of A and B, like here, we know this by now, it would be the total area of the two sets. And then if we wanted the complement, it would be this teal area here. So the area outside of the yellow area. This teal area is this term here. So A union B complement. Now let's look at this term on the right here. So we have the complement of A. So the complement of A will be any area outside of A. So it will be the area outside the two sets plus the area of B, which doesn't include A. The complement of B will also be the area outside the two sets, and this time it will be the part of A which doesn't include B. So we want the intersection of those two sets. So the intersection of those two sets, we'll do it in pink, the intersection of those two sets will be the area that is in both of those sets, the area where those two sets overlap. So where do those two sets overlap? The only region which was in both the complement of A and the complement of B was in the area that was in neither, so the area in pink that I'm doing now. So the area in pink will be the complement of A intersected with the complement of B. So we can see that the intersection of the complements of A and B is the area outside the two circles. So the complement of the union of A and B is the same set as the intersection of the complement of A and the complement of B. Okay? Let me just redraw the circles. So this is A and this is B. Okay, so now we want the complement of the intersection. So we already know what the intersection would be. It'll be the area where the two sets overlap, this almond-shaped type region here. So the complement of the intersection will be anything outside that almond shape. So it'll be this entire green area here. The green area here is the complement of the intersection of A and B. Okay, so let's look at the right side of the equation. So the complement of A will be any region outside of A, so any region outside this circle. The complement of B will be any region outside this circle. So it'll be that area and that area. So we want the union of those two things. So it will be any region that was in either of those sets. So let's do that in blue. So it'll be the region outside both circles. And so it'll be any region outside of B, and it will be any region outside of A as well. So it'll be that area as well. The only area that it won't include will be the region where we have both A and B. So the region where A and B overlap. So let's think about the significance of these two rules. So let's look at this one, for example. So the complement of the intersection of A and B is the same set as the union of the complement of A and the complement of B. So what if we were to take the complement of both sides of this equation? So let's take the complement of this side and the complement of this side. So we know from the previous video that the complement of A is just A. So anytime we have a double complement operator, we can just delete it and have what's on the inside of the double complement operator. So let's do that. And what are we left with? A intersect B is the same set as the complement of the complement of A union complement of B. So why is this important? It means that we can define the intersect operator in terms of the union operator and the complement operator. The same deal goes for this part of de Morgan's rule. The union of A and B complement, the complement of the union of A and B is equal to the intersection of the complements of A and B. Okay, again, take the complement of both sides, then by the double complement law here, we can delete the brackets and the complement operators on this side. So the union of A and B can be defined as the complement of the intersection of the complements. The complement of the intersection of the complements. Okay, so why is this important? Because it means that we can define the union operator in terms of the complement operator and the intersection operator. Okay, so this is important because earlier we had three operators, right? We had intersection, we had union, and we had complement. But these rules are telling us that we can define one of these, one of the intersection of the union, in terms of the other one. So we can actually just delete one of them, and we only need two operators. Say we get rid of the union operator, we can get by with just the intersection operator and the complement operator. Why? Because, well, we can define intersection as A intersect B, we can define complement as A's complement, and we can define the union. We still can define the union by just taking the intersection of the two complements and then the complement of that. Right? So now we don't have any less expressive power. We can still express all the same things, but we have one fewer operators. Okay, so anytime we write A union B, we are just abbreviating this longer expression here. And on the flip side, we can similarly redefine A intersect B as A complement union B complement complement. So instead of deleting the union operator, we could have deleted the intersection operator, just got by with the union symbol and the complement symbol, and defined intersection in terms of the other two. So this is telling us that we can reduce our inventory of symbols by one. We can delete one of the operators, union or intersection, and just define it in terms of the other one. So this rule, the set difference rule, is a little more simple. So all it is just redefining the set difference rule. So A minus B is equivalent to A intersect B's complement. This rule is pretty simple because we already know how to define A minus B from previous videos, right? So A minus B is just the set of things in the universe, the set of things X, such that X is in A, and X is not in B. Now, we know how to rewrite this term. So X is not in B. Well, that's just the same as saying B's complement. And then this and here, we know we can rewrite and as the intersection. So A minus B is really just redefined as the intersection of A and B's complement. So what is this telling us? Right? Earlier, we had 4 operators. We had the union, the intersection, the difference, and the complement. So we had 4 operators, but we know that we can define difference. We can define difference just in terms of intersection. So we don't need the difference operator. And then furthermore, we know that we can define union in terms of difference, right? Remember? Because A union B is just the same as the complement of the intersection of the complements. So we can delete union as well. So the key takeaway here is that we can eliminate 2 of the operators so long as we have the complement and one of the other ones. So here in this particular iteration, we've just stuck with the intersection operator. We deleted the union and the difference operator. Really, what the principle is telling us is that we can keep complement and we can keep one other one and define the other 2 in terms of them. So the key takeaway here is that all we need is the complement operator, and one of the others. If we have the complement and one of the others, we can easily define the other 2 using the set difference rule and De Morgan's rule. Now, that doesn't mean that we stop using the difference symbol or the union symbol or the intersect symbol. It just means that the union symbol can be considered an abbreviation of this longer term. Likewise, the difference symbol can be considered an abbreviation of this longer term.
Okay, so before we finish this video, let's do a couple of exercises, get some practice with writing proofs, because that's kind of a challenging kind of skill you want to build. So let's get a bit more practice with doing that.
Okay, so let's start doing some. This one is saying that A minus B union C minus B is equivalent to A union C minus B. Okay, so this looks a little hairy, but we can break it down. So let's start with getting rid of the set difference sign. So we use the set difference rule to replace the difference sign, right? So on both sides, C minus B is C intersected with B's complement. That's a set difference rule. Okay, now what do we do? Now we had the, what was it called? The distribution, right? So A intersected with B union C equals A intersect B union A intersect C. Right? So that was the, what was it called? Distributive. That looks like distributive, but distributive. Okay. So let's do that. We can just factor out the B complement, right? So just copying the format of the distributive rule. So wait, let me write what rule we use. So this was the set diff rule, and this is the distributive rule. So we've got B's complement intersected with both sides of the thing on this union, so we could just extract B's complement out and just have the union of A and C. Okay, now let's put B's complement on the other side using the commutative rule. So we know that commutative rule, we can swap the order of the arguments of an intersection specifically. Okay, and let's use the difference rule again to convert it back. Let's have another application of the set difference rule. going in the opposite direction this time to get rid of this B's complement. And we get A union C minus B. And then we've got what we have up there. So there you go, we proved that equality. Easy.
Okay, well that's about it from me. Thank you so much for joining me on this journey of set identities. Come back next time for another video about set theory. And if you like these videos, please remember, like, subscribe, hit the notification bell, leave a comment. Tell us what you want me to cover next. And thanks so much for watching.